So today we're going to be looking at 1.8, which is I can optimize a function and use this to solve real world examples. So part of the reason why that we find derivatives of functions is so that we can try and determine where those stationary points are so that we can find either a local maximum or a local minimum based on our question that we're getting asked. So, for example, we might be asked to find the function that's associated with building materials as well as the cost. So, of course, I want to try and find at what point am I going to receive a local maximum or a local minimum for the cost required of those building materials. So, of course, the derivative function is what's going to give me those local maxima and local minima. And I want to use these so that I can see, well, if I am going to be wanting to maximize my profit, then clearly I want to find when I have a local minimum of my derivative function so that I can find, well, at the bare minimum, I can have, this many building products so that I can try to optimize as much as I can how much profit I'm gaining from my business. So, of course, this process is called optimization, and what we're doing is pretty much looking to find the best possible solution. So this is a real-world application of derivatives and their functions. So, of course, we're going to be using differential calculus to be able to find the minimum and maximum of any function. So when we are solving these types of optimization questions, we want to make the process, I guess, as simple as possible for us. So the first thing you want to do is to create a labeled diagram if the situation is appropriate for it. So for instance, maybe you wanted to find the materials required to create a cake tin. So first off, you might actually need to draw a picture of the cake tin that you are going to be creating, and being able to label what points are the unknowns and what do I need to know to see if my cake tin, I'm going to maximize my profit. So that means making a cake tin as large as possible, but then also making sure that the cost of the cake tin is at its minimum as well. So trying to find that happy medium between the two of them. So of course, from there, once I have labeled that diagram appropriately, I'm going to have to create a formula for the situation. So when I construct a formula, I want to have the thing that I want optimized to be the subject, okay? So that was what your y is equal to, or what your, money is equal to, something. Okay, so that is the subject of my thing. And then, of course, I want my formula as a function to be in terms of a single variable. So making sure that there's only one x or, one y, there's not x's and y's all in the same formula. Otherwise, you're not going to be able to solve for one variable, okay, because you've got two unknowns rather than one unknown. And then, of course, we need to discuss the logical domain if necessary. So, of course, in terms of the cake tin, it might be unreasonable to be looking at possibly a cake tin that was, 100 meters long by 20 meters wide. Maybe we want to be restricting that domain to, reasonable cake tin sizes. And then, of course, once we've set up our function, we can then differentiate it. And, of course, remembering back when we did our finding our stationary points in our function, we need to find our derivative when it's equal to 0. So once we've done that, we will find where potential local maxima and minima are. And of course, to actually then figure out if it's a local maximum or minimum, I need to create a sign diagram and plug in points as necessary to see if I'm looking at a local maximum or local minimum, as well as checking my endpoints. So the two endpoints of your domain that you've picked, they could potentially be local maximum and minima there. So we need to check to make sure that that's not anything that is worth investigating. Then finally, once you have identified your optimal solution, just making sure that you write a sentence or a conclusion that actually answers the original question. So don't forget to do that. That is a very important part. What we're going to do next is we are going to have a look at a few examples, and I'll switch on over to my OneNote so that I can show you in a bit more detail.
This example is asking us to find the maximum area that can be formed by a loop of string that is 100 centimeters long and is formed into a rectangle. The first thing I'm going to do is draw a labeled diagram of the situation. Here is my rectangle. I'm going to make sure that I label the different sides. And as I don't know the lengths of my rectangle just yet, I'm just going to label this X and Y. Now, as I'm finding the area, I know that my area of a rectangle is length multiplied by width. Or in this case here, my area of this rectangle is going to be X multiplied by Y. The other thing I know is that my perimeter of my rectangle must be 100 centimeters, as the length of my string is 100 centimeters. At the moment though, my area here, or my area formula that I've got so far, is in terms of more than one variable, both X and Y. But I need to try and have it so that it's only in terms of X or only in terms of Y. So let's explore this perimeter a little bit more. So I know that my perimeter of this rectangle is all the sides added up together. So X plus Y plus Y. Simplifying this comes to 2X plus 2Y. And of course, I know my perimeter is equal to 100 centimeters. So I'm going to plug that into my equation here. So 100 is equal to 2x plus 2y. What I can do here now is rearrange this equation so that it's either in terms of only my x variables or only y. I'm going to rearrange so that I get y by itself. So in this case here, I'll get 2y is equal to 100 take 2x. And dividing both sides by 2 gets me y is equal to 50 take away x. So now that I've got this equation in terms of only a y, I can plug that into my area formula up here. So this is going to give me that my area is equal to x multiplied by 50 take x. Expanding these brackets out, I can say that my a of x, as it's now all in terms of just my x variable, is 50x take away x squared. The other thing I need to do is to also think about, well, what would my logical domain of this question be? Well, for instance, I know that my x value has to be greater than 0. I cannot have a side of a rectangle that is negative. That just doesn't make any sense. I can use my knowledge from my 50 take x here to try and figure out what my upper limit of x is going to be. Plugging that in here, I'll get 50 take x is greater than 0. Rearranging this gives me minus x is greater than minus 50. And now I've got to divide both sides by -1. And we know that when we divide an inequality by negative, it flips my sign over. So x has to be less than 50. Now this makes sense because if I had 50 in this equation here, it would be 50 take 50 is 0. And it would not be a maximum area if I'm doing x, or whatever length of x could be, multiplied by 0. I'd just get an area of 0. So that makes sense. So I can say that therefore, the logical domain has to be when x is in between 0 and 50. Now that we have our logical domain, we can find the derivative of our area function here. So area is equal to 50 take away 2x. And I know to be able to find a stationary point, I need to have my derivative equal to 0. So making 50 take 2x equal to 0, I'm going to rearrange this equation to find x. So minus 2x is equal to minus 50. And dividing both sides by minus 2 gives me x is equal to 25. So remember, now in this case, I now have a critical value, which is also known as my stationary point. So we need to see if this stationary point is a maximum or a minimum. And to do that, we need to create our sign diagram of my derivative function here. So rolling up a nice straight line, I'm going to put my 25 for my x value here. And also, I need to have my two endpoints from up here as well, because that's something that's worth checking. So 0 and 50, my two endpoints. So I'm going to plug in a number that is between 0 and 25 into my derivative function to see if it is a local maximum or local minimum. So see what's happening to this function on this side of my equation. So I'm going to put in 20, I reckon. So my area function when x is equal to 20 is equal to 50 take away 2 times 20. So that's going to be 50 take away 40, which is just 10. So as this is a positive number, then I know that my function at between 0 and 25 is increasing. And now I think for the other side, I'm going to look at between 25 and 50, I'll plug in 30. So my derivative function, when it's equal to 30, I'm going to have 50 take 2 times by 30, which is 50 take away 60. And of course, I'd get negative 10. So as this answer is negative, that means my derivative function is negative and that my original function itself is decreasing. So I'm going from an increase to a decrease, so like this. So I know that this point at 25, this is a local maximum, which is exactly what we were looking for. However, I've also got these two endpoints here, so I'm also going to check out potentially if there might be local maxima or minima here later on. So I know that we have a local maximum at x equal to 25. And remember, the original question is asking me to find the maximum area. So I need to actually plug this maximum or this critical value into my original function up here to actually see what is my area at x equal to 25. But I don't have a value for y yet, so I'm going to plug my x equal to 25 into this equation here to see what my y should be equal to. So using my y is equal to 50 take x from all the way up here, I'm going to plug in this x equal to 25 into my equation. So know that my length of my y side is going to be 25. So they're both 25 here. And now I can plug this value of 25 into my original a equal to xy. So this means my area is equal to 25 multiplied by 25. And I need to quickly grab up a calculator as I cannot do that from the top of my head. So 25 times 25 gives me an area of 625 centimeters squared. And don't forget, I also need to have a look at my endpoints. So when I've got y is equal to, let's quickly write down our endpoints. We know we've got the endpoints. And they are at 0 and 50. So I'll have 50 take away 0. So in this case, I'm going to have when y is equal to 50. So plugging this into my area equation. Of course, though, if I have my area is equal to my 0 times 50, I know that's just going to be 0. So that's clearly not a maximized solution. The other one is when my x is equal to 50 instead. So y is equal to 50, take away 50. So my y is equal to, in this case, 0. And of course, if I plug this into my area equation, I am going to get 50 times by 0, which will also give me 0. So of course, these two endpoints are definitely not a solution. So now that we know what my solution is, we need to look at the original question and make sure that we answer it. So it says, find the maximum area that could be formed using the loop of string. So I have found that, and my solution is right here. So I can say that, therefore, the maximum area that can be formed by a loop of string that is 100 centimeters long is 625 centimeters squared. Done.